for the following exercises. Find the point of intersection of each pair of lines if it exists. If it does not exist, indicate that there is no point of intersection. All right. So anytime we're dealing with problems like this, basically where we're given two equations, all right, and we have to identify how many points, or if there are any points of intersection, you really have to know these three rules off the bat. Okay, and I'll explain them. So rule number one, if the two lines, now remember, these are just equations, right? But these equations represent linear lines. How do I know that? I know that because they fall into the form y is equal to mx plus b. And I know that equations that fall into this category are indeed linear. If you still need a further reinforcement of why that would be linear, what you then would have to do is start just plugging in x values. Plug in x is 0, find out what y is. Plug in x is 1, find out what y is. Plug in x is 2, find out what y is. X is 3, plug in, find out what y is. And what you'll realize is that there is a linear then relationship between the values you're plugging in for x and the values you're obtaining then for y. So, it's just the way the math works, essentially. So, also now, what might be less obvious is this one. How do I know that that's a linear line? Well, I do know that I can do some algebra on this to get it into that form. Y equals mx plus b, meaning solve this bad boy for y. That's all I would have to do. Also, if that's unclear, what you can do is you can look at the variables that you have. I know I have an x here and I have a y here. They're both raised to the first power. Anytime you have just an x in the equation and a y in the equation, assuming that they're added together somehow, or subtracted from one another somehow, not multiplied or divided or anything like that, and they're both raised to a first power, it's going to be a linear line. Okay? So, the first thing I notice, again, is that these two equations represent linear lines. Once I know that, I can basically, and those are probably, we can assume, the equations you're going to be seeing in this class will be linear. All right? So let's go through the three rules. Okay? So first rule is that if the lines are identical, so if you have identical, I'll write equations. Remember, identical equations just mean that these lines then would be identical. So in other words, if I had a graph and I plotted, let's say, my red line, and the red line looked like that, the blue line would look like this. Okay? Oh, where'd the red go? Well, it's behind the blue. Okay? They're identical. So if I had something like that, identical equations have infinite points of intersection. I'm just going to do inter and then blah, blah, blah. My handwriting is, if you can imagine, this has actually gotten better over the years. So, identical equations have infinite points of intersection. In other words, take a look at the, well, I'd say, can I separate these two? No, they're literally right on top of one another. Okay, I can't. So let me do it this way. Let me just erase it. 1 second. So, okay. All right, it's not going to let me do it. All right, here we go. Let's draw the red line. Okay. And let's draw another blue line. I'm going to make it a little longer so I'll be able to grab it. Okay. And let's move that on top of it. Okay. So now this is the scenario where it represents infinite points of intersection. Remember, the two lines are exactly identical. Now remember, every single point on this line, on the red line, point. And the same thing on the blue, right? I can have a point there, point there, point there. Notice that if I now superimpose the lines on top of one another, in other words, that they had the same identical equations, well, those 2 points would have lined up if I could have somehow had the black points on the blue line stuck to it. Okay? Just imagine. So that's kind of what it means to be identical lines. Okay? They're literally on top of one another. All of their points will be in common. So they have an infinite number, right? I can draw an infinite number of points. All right. Probably like 2 minutes ago, you're like, all right, Andrew, I get it. Just get to number 2. Sorry about that. So the next one is going to be, so just remember in terms of the first one, I like to pair it up in my mind. Identical, infinite. Okay? Aye, Captain. I don't know how to make this interesting. So, next one. So we're going to talk about parallel lines, okay? Now, it also turns out, by the way, that that example, these also represented parallel lines, right? I mean, they had the same slope, right? If they're one on top of one another, just assume that they're perfectly on top of one another there. They also represented parallel lines, but it's even a step further. Okay, I know those lines are parallel, but I'm going to classify those two as identical. They are parallel, but they're really parallel and identical. All right, so maybe a parallel and the same we can call it. So maybe what I'll say here is, when I say identical equations, I know identical equations will always be parallel because they're the same. So they have the same slope, right? So identical and parallel. Well, forget it. I'm getting too technical. Just identical infinite. Easy enough. Now, if the equations are parallel, I'll say parallel equations or parallel slopes, and they're not identical equations and not identical equations have no points of intersection. Now that might start to make sense now. Imagine I graphed two lines. I had a red line and a blue line. All right, and if they're perfectly parallel, and they're not identical, right? Meaning, in other words, that they don't have the same y-intercept. Will they ever cross one another? Will they ever touch? No, they'll never intersect, right? So we know that parallel slopes or parallel lines, okay? Parallel lines, slopes, whatever you want to call it, doesn't matter. And they're not identical, meaning they have different y-intercepts. They will never have any points of intersection, okay? And then the third one. The third one is any case that does not fall into now case number 1 or case number 2. All those other cases, whether the lines now are, obviously they won't be parallel, right? They'll be at some angle relative to one another. They do have here a point of intersection now. Or if they were perpendicular, let's just say perfectly perpendicular, you might say, well, they're not intersecting. But remember, the lines really continue on forever, right? So this line would have really extended on, and they do intersect at some point. So in other words, what I'm going to do here is just erase this. So in other words, any other case here, all other cases, C comes before A, all other cases have one point of intersection. So really there's three answers to a question like this, okay? Either they're going to have infinite points of intersection, they're going to have no points of intersection, or they're going to have 1 point of intersection. So if you didn't know anything, you get a 1/3 shot, okay? But we want to know something. So we want to know what to do with this. Now remember, basically what I want to do first is I want to actually kind of go through this as like a checklist, 1, 2, 3. So first thing I want to do is I want to then see if these lines are indeed identical. And the only way to do that is to put them both, if they're not already, put them both into this form of y equals mx plus b. Okay? And then let's see what's going on from there. So hopefully you wrote this down because I'm going to erase it. And if you didn't, that's the beauty of YouTube. The rewind. So let's take that and negative 3x plus 4y is equal to 12. Let's put that in y equals mx plus b. I know I got to move the x on over to the right-hand side. So I'm going to add the 3x to both sides. Right? That just cancels. Bye-bye. So then we got 4y is going to be equal to 3x plus 12. And then we got to divide both sides by 4. So y now will be equal to 3 over 4 x plus 12. Great. What? 3 over 4x plus 12? I'm just seeing if you're paying attention. You paying attention? Did I trick you there? Now remember, I'm running through this. I apologize. My mind is already like trying to identify whether they're the same, identical, or parallel, or whatever. So we can distribute the 4 to each of the numerator terms. So that's how I got the 3/4 x. Okay, 3 over 4. And then the y-intercept basically portion would be 12 over 4. And what's 12 over 4? it's simply going to be 3. Okay, so this is plus 3. Just seeing if you're paying attention. Okay, so now that I got both of these equations here, I'll box both of them now. I got both of them in y equals mx plus b form. The next thing I'm going to do is find out whether they're identical. They got to be identical. When I say identical, I mean identical. Okay, are these two exactly the same? Exactly the same. No. How are they different? Obviously, they have different y-intercepts, right? So that would be like something like this. That'd be like if I had this line here has a y-intercept of 1, so that looks about right. And this line has a y-intercept of about 3, right? So I'll draw it like there. Right, 3 up here, 1 over here. Okay. Now, what do I notice though that is actually the same between them? I do notice that the slopes are the same though, right? So here the slope of the first one is going to be 3/4 x, and the slope of the second one is also 3/4. So they are indeed parallel. So since they're parallel and they are not identical, meaning they have different y-intercepts, how many points of intersection will they have? Zippo, right? 0. 0 y-intercepts. In other words, the proper answer to the problem would have been no point of intersection. Okay? It's literally that simple. So now, let's run through the second example. Okay? I always like to take time on the first one, show you how it works, and then we're going to see how, not necessarily quickly we can apply it, but, knowing the ropes, we're going to apply it a little faster. So now what I want to do, I realize I got two linear lines. Again, both have an x and a y in it. They're both raised to the first power, and they're both added or subtracted from one another. So what I'm going to do first is I want to figure out whether they are identical or not. I'm going to put them into the y equals mx plus b form. Okay, so let's take the first one. 2x minus 3y is equal to 12. Solve this for y. So subtract the 2x on over to the right-hand side. So it's going to be now negative 3y is going to be equal to negative 2x plus 12. And divide both sides now by negative 3. When we do that, we realize that we get y now will equal, again, distribute the negative 3 to each of the two terms in the numerator. So there's going to be now positive 2/3 x, positive 2/3 x plus, minus 4. Okay, let's box that. Second equation, I realize it's also not in y equals mx plus b form, so I'm going to do that. Right, so let's write it out. So 5y plus x is equal to 30. So let's subtract the x on over to the, right-hand side. I had to think about, what's your right, Andrew? What's your right? Plus 30. Okay, then divide both sides now by 5. All right. So here we get y is equal to then, basically now, so we, again, going to distribute this 5 to each of the two terms in the numerator. So and remember there's like a hidden coefficient there of 1 in front of the x. So it's essentially negative 1/5 x plus then 30 over 5, which we know it to be 6. All right? So now, these are both in y equals mx plus b form. Are they identical? Are they identical? Is this thing the same as this? Definitely not, right? Not the same. Okay, next thing to check are they parallel? Is it parallel? Nope, different slopes. Okay, so that means, guess what? They do have 1 point of intersection, right? Remember, that falls into the third category. Now, they have exactly 1 point of intersection. The question is, what is it? How do we find it now? Okay. It turns out that all the work we did was not for nothing. Watch. So let's just erase some of this, okay, now that we have our two equations. And recall that, 1 second. How you guys doing today? Hopefully you're having a good day. All right. So there might be some mild turbulence ahead, but don't worry, we're going to fly through it. So, remember that, let's pretend I have a graph and I have two lines. Okay, I know this is a positive slope, this is a negative slope. I know they get, actually, you know what, I'll try to do it a little bit to scale. This is a y-intercept of negative 4, so that means it's about here. It's had a positive slope, so maybe it looks something like this. The red, I'll put a little red check there. Okay, this one is in blue, so I know it has a y-intercept of 6, which is up here. I know it's a negative 1/5 slope, which is pretty shallow, so maybe it's something like this. Okay, and what I'm going to try to do is make that a little flatter, and I'm going to extend this out a little bit. Okay. Now, by the way, this is roughly to scale. I have no idea if, this coordinate here will be the coordinate of intersection. Meaning, in other words, that if we were to extend the x-axis on out, that this point falls into the first quadrant here, right? This is the second, the third, right? And then the fourth. I have no idea if the two coordinates will be positive, all right? But I can probably be relatively certain that they should fall either within the first or the fourth quadrant. Right? So in other words, that the x and the y value should be either positive x and a positive y, or if that point of intersection lied down here, it would have been a positive x and then a negative y. If I'm getting negative x and negative y or something, right, which would be quadrant 3, then I'm definitely off the mark. All right. So what I do know, though, so let's just back out of this. Okay. What I do know is the fact that these two lines will have one single point here of intersection. I know that for a fact. Okay. Now notice that the point here is in common amongst the red line that we drew over here and the blue line that I represented like this. I forgot my little check mark. What that means is that the x and the y coordinates of this, let's just assume that they're positive for now. I'll just call it xy, okay? I know that whatever the x value is of the red equation, okay, because of the red line, is going to be the same as the blue one. And the y value of the red line is then the same as the y value of the blue line. In other words, this y is the same as this y. And this x is the same as this x. So what does that mean? Well, what that means is now we can do a substitution, okay? And BTW, there's many ways to solve this problem. Your professor or teacher might say, hey, just add these two together and we'll go about that way and we'll do an addition. That's great. That's fine. Fantastic. Wonderful. However, though, when you get further along in math, you're going to realize that that particular method has some limitations. I'm going to teach you a substitution method that really doesn't have any limitations to it. You can apply this in many, many contexts. So why don't we develop good habits at the start? Let's not take the easy road. Let's take the road less traveled, right? And if anybody knows that poem, beautiful poem, who's it by? Leave a comment. All right. That way I know who's watching the video. What? All right. So what I realize now is that this y is going to be the same as this y. What that means is that if y here is equal to this, and this y is equal to this, well, that must mean that this whole part is equal to this whole part. Because y is equal to y, right? Y is equal to y, and whatever then y is equal to must also be equal. And now look at the beauty of this. Watch. This is a substitution, basically. I'm basically, you can think of this. I'm taking this and substituting it on here for y. Or I'm taking this and I'm substituting this on in for y in the other equation. I'm doing a substitution. So watch the beauty. So 2 over 3 x minus 4 will then be equal to, okay, so essentially what I'm doing, if just to follow perfectly, I'm taking this essentially, I'm going to plug it on in for this y. Okay, that's what I'm going to do. So I just wrote that y on out, right? And now that is equal to the other part. Negative 1/5 x plus 6. Take a step back, ladies and gentlemen. What do we have? We have one equation with one unknown. It's beautiful because we can solve that, right? This is solvable now. And remember, we said before that whatever x is in this equation is the same as the x in this equation. And then I know these two x's are identical, and if I can find it now, that means I know what x is. I know the point of intersection. Okay? I think I'm just hitting puberty again. I don't know. Anyway. So plus 1/5 x plus 1/5 x. And how do we do it, right? So remember, we're going to add fractions. We need common denominators, right? You could probably just do this in your calculator too. It really doesn't matter. But why don't we do common denominators? So I'll do this on the side. So this will be 15. The common denominator is 15. I got to multiply 3 by 5 to get to 15. That means I got to multiply 2 by 5, and that'll give me then 10. I realized that I had to multiply 5 by 3 to get to 15, and therefore I got to multiply the 1 by 3 to get to 3. And then I can now add these two bad boys on up. And what are we going to get? We're going to then get 13 over 15. Remember, keep the denominators there. And what I'm also going to do at the same time, so I did that. And I also want to move this on over to the right-hand side. So I'm just going to kind of do that in one step, right? So I'm going to add the 4 then on over to the right-hand side. So I know the 4 is canceled. Let me put that actually in red. The 4 is canceled. This would have canceled as well. So what I'm then left with is then equal to now 10, right? Because the 6 plus the 4 is 10. And now all I kind of need to do is well, we can think about doing like a cross multiplication here or whatever. You know, you can take this side then and multiply it by 15 over 3. 15 over 13. Take then this side and multiply it by 15 over 13. All right, and then we would get our answer. So here we have now x being equal to, this is going to be 150 over then 13. Okay, now this is a decimal, right? I mean, it's a fraction. It's a fraction, but if you don't like that number the way it's written, you can definitely convert that into a fraction. Into a decimal. So how would you do that? Well, you would simply take 150 and then divide it by the 13, and that comes out to about 11.5. All right, so if you wanted, you could do that. So x is approximate, I'll put it up here. X is going to be equal to 150 over 13, or in other words, about 11.5. All right, so that is our x value here. All right, now let's do the same. So now that we know x, how do we find y? This is simple now. It does not matter which equation you choose. Okay, you can plug in this x value here into either equation you like. Actually, I'll do it for both, and watch, we're going to get the same y value because the y's are the same, so this should all work out. Watch. Ready? So y will be equal to 2/3 multiplied by the x, which is 150 over 13, minus 4. All right, what I'm going to do is I'm going to plug this on into the calculator, okay? So we're going to do that. Multiply it then by 2 over 3, and then we're going to subtract from that 4. So this comes out to about 3.69. I'm just going to use decimals. 3.69. Okay? Now, I'm going to do the same thing for the other equation. So watch. Y will be equal to negative 1/5 times then, what do we got here? 11.5? Well, let me do the exact fraction again. So there's 150 over 13. Plus 6. Let's plug that into the calculator. Let's see what we get. Just be careful with the signs. All right, so we're going to get, 1 over 5 times then 150 over 13. That'll be negative, right? Negative 2.3 or so. And then we'll take 6 and we'll subtract we'll take 6 and subtract 2.3 from it. And what do we get? We get about 3.7 now. Now, I'm rounding here, okay, 3.7, so I'm just using my phone calculator. But notice that, you know, these are basically, this is the same answer. I'd say, well, it's off by a decimal. Well, that's because I'm rounding. But these are identical, essentially, okay? If I took it out with actual fractions and I did it, you'd notice that the fractions are identical. So, the answer is, so the point of intersection again, this is it. This is the point of intersection, right? What I'll do here is I'll write the y up here. Y is equal to about 3.7, okay? Now go back to our graph that we had before. All right, if you're still with me, God bless you. Okay, that means you really want to learn. So, and which is great, by the way. So that's how I'm trying to explain this. Somebody who really, really wants to learn. So the y-intercept down here for this equation was a -4, and the slope is about 2/3. So that looks good. The y-intercept here was 6, and the slope is going to be -1/5, so maybe it's somewhere about there. Okay? This is, again, not at all to scale, but we said that the point of intersection might be where x is going to be positive and the y value is going to be positive, falls into the first quadrant. What do we get? And that's what we got, right? We got that x is 11.5 positive and y is about 3.7. But doesn't this even look kind of to scale-ish? Right? X is 11.5, meaning it goes out 11.5 units on the x, positive, and then it goes up, positive, 3.7 units. Yeah, right? So I pretty much know, I mean, that's how I'm checking. But it's going to be right. Okay. All right. So this problem is very important. It's actually a very easy problem not to understand, but it's a very easy problem after you do some practice. All right. It's just very rote, but you got to understand what's going on. So I really do hope that this helped. All right. And what we've been doing also is we have been cataloging these particular videos in a playlist, all right, in playlist fashion. So I would highly recommend you check out either in the description or if you go back to our channel and you look at some of the playlists. This video is going to be found in basically a linear function playlist where any problems you might be having with linear, equations and whatnot in your pre-calculus or algebra course or whatever the case is, check it out. I think you'll find it very useful. And guys, thank you so very much. Appreciate it. Please remember to subscribe and hit the like button to help us out. And I look forward to helping you with more problems. Be well.